you have any kind of stimulus, you get a reaction at first and then adaptation. If you add more stimulus, then you'll get response again, you'll get reaction again, and then adaptation. So you can add stimulus several times, but sooner or later, it stops. You can't do it forever. Sooner or later, the whole thing becomes saturated and it won't react anymore.
Is that like the idea for using antibiotics or properties of antibiotics?
No, that's something different. That's something different. That's actually, frankly, evolution. If you remove the attractant, everything goes back to normal. If you remove the repellent, everything goes back to normal. That's actually not very significant. It just says, take away the repellent, now it starts tumbling every 2 seconds. Take away the attractant, starts tumbling every 2 seconds. So basically, without the stimulus, things just go back to the way they were. So not a very major comment there. Now, E. coli, now we haven't seen that before. Escherichia coli, but everybody just says E. coli, is probably the most common bacteria that we will use in the lab. We'll be using it all quarter. It's normally paratrichously flagellated, so flagella all over the place. But there are types that are monotrichous, so one flagella. So this guy that I actually know did this fairly neat experiment. He put the bacteria into, so the pieces of flagella came back together, and now he had flagella without the bacteria.
Weird.
What? Yeah. And then he took these flagella and he injected them into mice. Now the idea here is that these are foreign particles, yeah, flagella, but foreign particles into any type of organism, the immune system will attack it. It was exactly what happened. Well, the flagella is protein. So what was formed were antibodies to attack the protein. And then the guy just took out blood samples from the mice and was able to isolate the antibodies. So in other words, he had flagellum antibody. So again, he just simply dissociated the flagellum from the bacteria by putting it into salt, and then isolated the pieces, put them into mice. The mice made antibodies, and blood sample, he was able to get the antibodies. So what happened then? What happened then is he got a beaker of solution, and he put in some E. coli, and he put in the flagellum antibody. So there's your E. coli, and then the antibody grabbed onto the flagella, because after all, that's what antibodies do. They grab onto the antigen. And for the antibody, the flagella was the antigen. And then most antibodies will grab or bind onto smooth surfaces, if they can. And that's what happened here. So the flagellum antibody bound on one end to the flagella, and on the other end to the beaker, to the glass wall of the beaker. In other words, the bacteria was attached to the beaker. So why do all this? Well, think back last week. Think back last week when you were looking at the wet mouse, and most of you did find bacteria. But many of you had trouble keeping track, because the bacteria would be swimming all over the place, and half the time they would swim out of your field of vision, and you had to start moving the slide around a little bit to find the bacteria again. Well, when the bacteria here is glued to the wall, it's not going to go anywhere. So this antibody is essentially acting like glue, attaching the bacteria to the wall of the beaker, so it could not swim. So then he was able to get one of these big old magnifying glasses, and you could literally watch one single bacteria. It was a clever setup. So the antibody binds to the flagella and then to the glasses. But the point of all of this is he added attractant to the system, and he found that in the presence of attractant, the flagella rotates counterclockwise. In the presence of a repellent, the flagella rotates clockwise. What? Counterclockwise and clockwise. Now this answers a question: when there's an attractant or when there's a repellent, how does the bacteria even know? How does the bacteria know that it is an attractant, or that it is a repellent? This is the answer to that question. Because the bacteria knows depending upon which way does the flagella rotate. If it's rotating counterclockwise, it's got an attractant. If it's rotating clockwise, it's got a repellent. The question is, how does the bacteria even know that there is an attractant or a repellent?
So the flagella, knows more than the bacteria itself?
Yes.
It's not the bacteria that does.
Yes, the flagella is able to respond better than the bacteria to what stimulus you got. Yes. But you touched on another question. Now her phrasing was the flagella knows more than the bacteria. That's not really too far off. That's kind of correct. But it does raise the question, how does the flagella know if it's got an attractant or repellent? How does the flagella know which way to rotate? That would be the next question.
Protein.
What is a protein? The flagella is a protein. But anyhow, the bacteria knows attractant or repellent based on which way does the flagella rotate. The next question would be, how does the flagella know which way to rotate? So that's going to be where we're going next with all of this. Like I said, there actually is a goal, even though, first off, you may not care, and second, you don't really see where I'm going yet, but I am going somewhere. So, the flagella, as it's rotating, it can change direction. It can change direction. And when it does that, it causes tumbling. Now, I've got that here. Tumbling is caused by a switch in rotation from counterclockwise to clockwise. Now, it can be the other way too. I just put one on. It can also be from clockwise to counterclockwise. Basically, if the flagella changes direction of rotation, you get tumbling. That's what causes the tumbling.
But, so you're saying that there would need to be an attractant and a repellent every 2
Possibly.
seconds? 4
Possibly.
seconds?
Possibly. What's actually quite amazing about this is the chemotaxis response is temporal. That means time dependent. What that means is the bacteria can actually remember the past environment. And that would raise an obvious question, how can a one-celled organism remember anything? Well, it does.
Because they're clones.
I'm sorry?
Because they're clones.
No, actually not. That's a good suggestion, that, frankly, but that's not the reason. It's a different thing. If the bacteria approaches an attractant, there'll be a bacteria, there will be an attractant of some sort. So it's an attractant. The bacteria swims towards the attractant. But the fact is, it is a bacteria. There's no GPS system. So sooner or later, within a few seconds, it's going to get lost. It will go off in the wrong direction. And this now will be an answer to the question where I put you on hold. As it's swimming towards the attractant, it's kind of like going toward a campfire. As you're walking toward the campfire, even if you can't see it, but the heat is building up. You can feel the heat as you get closer and closer. So the bacteria can sense the attractant as it gets closer and closer. You can get a stronger signal. But then it starts going off in the wrong direction. So when it goes off in the wrong direction, now the signal is no longer getting stronger. It'll start getting weaker, which means it's going away from the attractant. That makes the rotation change direction. It goes counterclockwise as long as it's going towards the attractant. When it stops going toward the attractant, the rotation changes. Now it goes clockwise. That causes tumbling. So once it stops going in the direction of the stimulus, then the bacteria wants to change direction. It's kind of like, well, I was thinking of the campfire again. It's kind of like the campfire, even if you cannot see it, but if you're walking toward the campfire, it's getting warmer and warmer, and then you start going off in the wrong direction, even though you still cannot see it, you can feel that it's no longer getting warm. You're starting to get cool. So if you start to get cool, you change direction, and you start going off in the direction where it's getting warmer. Well, that's kind of what's going to happen here. Once it starts going off in the wrong direction, it needs to change direction, but it cannot turn like we do. It cannot just physically turn. So the way it changes direction is the tumbling. That is how it changes direction. What causes the tumbling is when the direction of rotation changes. So as long as it's going toward the attractant, the flagella is rotating counterclockwise. Once it stops going toward the attractant, then it goes in the other direction. It goes clockwise. But in changing direction, that makes it tumble and now facing in a new direction. But the tumbling is random, which means it doesn't know where it's going to stop tumbling. So it very well might face the wrong direction. When it finishes tumbling, maybe it's facing that way. That's where this memory thing comes into play. The bacteria remembers there's a promised land. And it knows it's not facing the right direction. So it will tumble again. It doesn't even go anywhere. It tumbles again, and it will keep tumbling until it faces the right direction. Yes?
Basically what you're saying is your interpretation.
Yes.
Really inefficient.
Very inefficient. That's why it's a bacteria. Yes, very inefficient.
I'm a little confused because I thought the way it tumbles is pretty, the frequency is consistent throughout.
Sure,
So-
except now with the stimulus. See, with the stimulus, it changes. Her question is that what I was giving all of you earlier, is that it seemed to be fairly consistent. But in this situation, we're first going towards an attractant, and then we're not. That changes the frequency.
So what I meant is, once the stimulus is added, like when the attractant is added, it becomes more frequent, but I didn't understand that when it's going closer, that all of a sudden the frequency changes as it's going closer.
It can. It can. In a perfect world, it wouldn't. In a perfect world, it just keeps going toward, and the frequency would never change. But it's not a perfect world. So as the bacteria keeps getting lost, the frequency will change. The frequency will change. Yes? It's going to get lost again. It has not evolved yet. It's still a bacteria. So it once again will go off in the wrong direction. Once again, it's going to start tumbling. Until it gets there. Like he was commenting, it's pretty inefficient. It's pretty inefficient.
But once it feels as the example you used, the warmth of the campfire, it doesn't tumble as often.
Correct. Exactly
goes
right.
straight. So then if
Exactly.
it's a repellent, because it doesn't know which direction it's going, it just keeps tumbling all the time.
Yes, exactly right.
But it's still gonna tumble every like 4 or 5 seconds. no matter what.
It will, it's a bacteria. It's going to get lost. And the tumbling every few seconds reflects that sooner or later it's going in the wrong direction and it's got to tumble again to start facing the right direction. And remember, it cannot control how it tumbles. I mean, all of us, of course, we just turn. They can't do that. So when it finishes tumbling, who knows where it ends up? And if it's facing the wrong direction, it's got to tumble again. Like he commented, not very efficient. There's a reason why it's a one-cell organism. These guys don't go to college. Yeah, not efficient. So, it'll both be attracted, it's gonna get lost a little bit, it'll tumble. If it faces the wrong direction, it's got to tumble again until it faces the right direction. The point is, it remembers there is a right direction. So it'll keep tumbling until it's facing the right way, and then off it goes again. Doesn't sound like fun.
Can you remind me again what the goal of the
I'm sorry.
bacteria is?
What?
Remind me again what the goal of the bacteria is.
To get to be trapped.
Give me an example of different, like a try to food to kind of
Sugar? Food?
to
Food?
do what it needs, like,
Yeah,
Surviving.
yeah.
and not just for survival, but just, well, I guess for survival. when it-
Well, food would
because it
be,
wants to-
would work. Or any building supply of some sort, anything it needs would be an attractant.
So
Again, food's an easy example, but,
So I'm thinking
anything.
like the purpose is to grow.
pardon me?
I'm thinking the purpose is to grow
Sure.
faster.
Sure, yeah,
Okay.
that would work, yeah.
Now, would food be in this situation a chemotaxin?
Well, it's all chemotaxis.
Okay.
The chemotax is simply dealing with a stimulus from chemicals.
Okay.
And food is a chemical. I mean, yeah, we think of it as food, but it's really just chemicals that we're eating. Yeah,
Does it do the same thing to get away from?
yes. Our question is, does it do the same thing with the repellent? Will it try to get away? Yes. And then it'll still get lost. So it's got to do this all over again.
It'll continue to tumble until it reorients itself
Correct.
away from the repellent.
Life of a bacteria.
So I don't know what you said for the answer for why the flagella, how the flagella knows what to go towards.
I haven't answered it yet.
Oh, okay.
Yeah, she said, she actually caught on to something I was trying to slide by. When I was saying, the next question would be, how does the flagella know which way to rotate? Well, I didn't answer that question,
Okay. I thought it
and she caught on, so I still haven't answered it. I'm going to later.